Okay, I wanted to show you how to use this integrated rate law. And so sometimes you get a problem where they want you to uh, find out how much of something is remaining after a certain period of time. Or they could ask you how long something it would take for something to change into something else. And so there are some equations on the AP formula sheet, and it's shown under the kinetic section. And so then there's three equations that they give you. Now we've already talked about the half-life equation, but the top one here is the one for the first order rate law and or for a first order reaction, and the next one down is for a second order one. If you remember the graphing, how we linearize like a graph, if a graph was concentration over time and it was curved, remember that if it was concentration over time, that you could take the natural log of the concentration over time, and then that would straighten it out if it was first order. And so that's the first order one there, that's the second order. Now, when you do a problem like this one right here, you have to figure out which one you want to use. And when it says it's first order, well, you want to use the first order equation. Another way to tell you if they don't tell you it's first order, a first order rate constant, so the k for first order is always going to be something like time to the negative 1 power. Okay, so like seconds to the negative 1, minutes to the negative 1, or hours to the negative 1, or something like that. And so the equation goes like this. The natural log of concentration of A at a given time period after so much time has went by minus the natural log of the concentration of A at time 0, so that's like the initial concentration, equals a negative rate constant K times the time T. All right? So anyway, you might want to go back through and review what these variables mean. I just said them, but you could replay the video. But anyway, all right. So anyway, what you got to do is you got to read this and plug in. And so it says plug in the numbers. How much of a 5 molar sample will have reacted? So I think I want to change this to will remain after 75 seconds. All right, and so this is how much will remain after 75 seconds. That's a little bit easier than figuring out how much has reacted. But anyway, okay, so anyway, you read this, and so it says, how much will remain? So that's what this one is right here, like how much would be remaining after a given time period. All right, and so we're going to be looking for the concentration that will remain after a given time period. We're going to subtract how much did we start with. Okay, so to begin with, it says that it's 50.0 e to the negative 3. That's how much you started with, and I forgot, I need to take the natural log of that. I forgot to write that. So the natural log of 50 e to the minus 3 will equal a negative k. So does it give us the k? Yes. So a negative 4.5 e to the minus 3 seconds to the negative 1 times the time, and that's going to be seconds. Now, one critical thing is always make sure that the rate constant and the time unit that you're given in the problem, make sure the units match. That should be just seconds, not seconds to the negative 1. Seconds, seconds to the negative 1. So that way, what will happen when you multiply them together, the seconds are going to cancel out. If this happened to be hours, you would have to change that. So anyway, if I do some math here, I'm going to get the natural log. So I'm going to just write this over. The natural log of substance A, the molarity of substance A, or the concentration, minus, now I'm going to do the natural log of 50 e to the minus 3 on my calculator, and that's going to be equal to a negative 3.00, okay, is going to equal, so I'm going to take this 4.5 e to the minus 3 times 75 seconds, and that's going to equal a negative a negative 0.3375. I guess I didn't fit something like that. Okay, and then your seconds will cancel out. Now, remember that when you have a natural log of a to sometime t, a negative and a negative makes a positive 3. That's going to equal a negative 0.3375. We got to move this 3 over to the other side, so we're going to subtract it from both sides. Okay? Now remember, when you're subtracting, you're going to end up really adding them together in a way, so because you got two negative numbers. So the natural log of a to t is going to equal a negative 3.3, and I'm going to round to the significant digits, 34. Okay, now you have to get rid of the logarithm here. So to do that, you will get a to the t will equal, you'll do second log on your calculator, or it's the e to the x button. And so e to the x, and the e will be a negative 3.34. And so that's like hitting the second log button. And what you should get, if you work all that out, and that's going to be equal to around 0.035 molar. Okay, so that should be the concentration when you get done. All right. So that's how to do that. Okay. Here's a second problem. All right. So the decomposition of a 0.1 molar sample is first order. Okay, because it's first order, we're going to want to use the first order rate law equation. All right. So what we would do then is we would use this equation, natural log a to sometime t minus natural log a sometime, that's at the time 0, that's like at the beginning, the initial concentration, equals a negative rate constant times t. Okay, now why don't you pause your video and see if you can plug in the numbers and see what you get by doing this, and then you can restart the video and see if you get what I get. Okay, so let's see what you get. So it says what will be the concentration after 150 seconds have passed. That means we're looking for the concentration of A after a certain amount of time. We're going to subtract the natural log of the initial concentration, and then that's going to be equal to a negative K, so they give us the rate constant. Don't forget the negative. That's kind of one thing that I tend to do sometimes that you don't want to do. Okay, times the time, and I should always write the units. I forgot to write that. Seconds to the negative 1. And you're going to multiply that times the time, because you want to make sure that these units, when you multiply these numbers, are going to cancel. You can't have like a minute here and seconds to the negative 1 there. Anyway, so then what would happen is you would get the natural log of a to a certain time t minus the natural log of 0.1, and so that's going to end up giving you negative 2.3, and then that's going to equal 6.93 e to the minus 3 times 150, so that's going to equal a negative 1.04. Okay, remember when you got two negatives, that makes a positive, so I'm just going to make that a positive here. So then to move it to the other side, I'm going to subtract 2.3 from both sides. And over here, you're basically adding them because they're both negative. So you get natural log of a to the t is going to be equal to a negative 3.34. So to get rid of the natural log, you need to take e to the x to both sides. So that's going to equal e to the x, a negative 3.34, which is the same thing as hitting second log on your calculator. And then you would get that the concentration then is going to equal 0.035 molar. Okay, that's how to do one of those types of problems.